Before we try to implement unify, let's look at some examples. Again, this is a simplified unify where I don't bother with the expression to complain about. I just have the two types that unify makes sure are equivalent. If unify gets int t and int t, it should succeed, and so that means just returning void, right? Int t is clearly equal to int t. There are no type variables to adjust. Similarly, bool and bool, those unify just fine. If I have int t and bool t's, though, this would be replacing a check that int t and bool t are the same and complaining if they're not the same. So it's unify's job to complain. It'll raise an exception that says no type. If I give unify a type variable and integer type, and if that type variable is not equated to anything so far, then unify will succeed. Behind the scenes, it will also change this box, but our example here doesn't demonstrate that. It just shows that unifying int and an unconstrained type variable will succeed with void. On the other hand, if unify gets a type variable that has already been equated to something, it will need to check. And if that variable is already constrained to be an integer type, that unifies just fine with integer. But if the type variable has been equated to Boolean, then Boolean and int don't go together, and so unify will raise an exception at that point. But this is just showing what happens with different varieties where you don't have examples that show how it changes. So let's try to make that kind of example. Here I am defining t as a fresh type variable. I'm unifying it with int, and then I'm trying to unify it with bool. And in this case, we get an exception, no type, because the type variable can't be both int and bool, and in fact, it's the second call to unify here that will complain. On the other hand, if I try to unify t twice with int, that's all consistent, and so unify will be happy in both cases. If a type variable is unconstrained, and then we use it inside of an arrow t, unify's job will be to go inside the arrows and make sure everything is okay too. So the result types are bool and bool. Those will unify both fine, but a recursive call will unify t with int t, and so it will be setting t internally, and then when we check again whether t is int t, that will pass. On the other hand, if I have an arrow t with a t inside of it, and I try to unify it with just t, this is where the occurs check will take effect, right? We will want to assign an equivalence that says t equals arrow t, but t is inside of that arrow t. And so the occurs check should say that it occurs, and unify should refuse to install an equivalence. If I have two different type variables, both are constrained, then unify succeeds. It sets one of them equal to the other. We don't specify here exactly which one gets set to the other, because it's not going to matter. We're talking about equivalences, and things run in both directions. Unify will pick some particular direction, though, rather than creating cycles between two different variables. If we unify t1 and t2, and then we also unify t1 with int, then t2 somehow inside is also unified with int. And so trying to unify t2 with bool after that should produce no type. So this example illustrates how this unify does set up a connection between t1 and t2. And it doesn't matter what order we do them. If we unify t2 with bool first, then we still fail, and when we later try to unify t1 with int. One more example with arrows. So here I'm unifying t1 with t2 arrow bool t. So what we know from this is that t1 is an arrow whose result type is bool t. And then later we unify t1 with arrow, so far so good. Result type t2, well, that could be fine, except we've also said that t2 is the argument type of the arrow t1, and now we're saying that the argument type is int. So t2 cannot be both int and bool, and unify will complain at the second case here. So we need to implement a unify that handles all of these different possibilities and recurs inside of arrows and sets up equations between type variables and so on.